Dear students, I am Dr. Rachna Mathur, Associate Professor, Dungar College, Bikaner. In the series of lectures on the topic Operation Research, which is part of syllabus of MSc Final, we are going to study linear programming problem in this lecture. So, first of all, we come to the introduction of the linear programming problem. George Denching and his associates in 1947 found out a technique for solving military planning problems while they were working on a US Air Force project. This technique consisted of representing the various activities of an organization as a linear programming model and arriving at an optimal program by minimizing a linear objective function. He also developed the most powerful tool known as simplex method to solve linear programming problems. An organization has at its disposal men, machines, money and materials, the supply of which be limited. The management must find the best allocation of its resources in order to maximize the profit or minimize the loss. Linear programming can be used if the following conditions are satisfied, in which first is there must be a well-defined objective function, maybe profit or cost, which is to be either maximized or minimized and which can be expressed as a linear function of decision variables. Second one is there must be constraints on the amount or extent of attainment of the objective, and these constraints must be expressed as linear equality or inequalities in terms of decision variables. And the third one is decision variable should be non-negative. Now we come to the mathematical model of LPP. So first of all, we talk about the objective function. Maximize z equal to c1x1 plus c2x2 plus cnxn. Subject to the condition a11x1 plus a12x2 plus a1nxn less than equal to or greater than equal to b1. a21x1 plus a22x2 up to a2nxn is less than equal to or greater than equal to b2, and so on. m1 am1x1 am2x2 plus amnxn less than equal to or greater than equal to bm. And third one is non-negative restriction, which may be written as xj is greater than equal to 0, where j equal to 1 to n. In matrix notation, we can write maximize z equal to cx, ax is greater than equal to or less than equal to b, and x greater than equal to 0, where c equal to a row matrix c1 c2 cn, which is called price vector, b equal to a column vector b1 b2 bm is called requirement vector. A is a m cross n matrix, a11 to a1n, am1 to amn is called coefficient matrix. Now to explain the problem, I will take an example. A manufacturer of furniture makes two products, chair and table. Processing of these products is done on two machines, A and B. One chair requires 2 hours of machine A and 6 hours of machine B. One table requires 4 hours of machine A and 2 hours of machine B. There are 16 hours of time per day available on machine A and 20 hours on machine B. Profit gained by the manufacturer from a chair and a table is rupees 3 and rupees 5 respectively. So we have to formulate the LPP for the daily production of chairs and tables so as to maximize the profit of manufacturer. Now, in order to formulate mathematical model of the problem, we prepare a table. You can see on this screen, we write in first column machine AB, and then how much chair and table are required, hours required. We can write this chair required 2 hours of A, 6 hours of B, table require 4 hours of A and 2 hours of B. And in the last column we are given hours available of machines A and B in a day. For A it is 16 and for B it is 20. Now we also write here profit in rupees for chairs and table. So it is 3 for chair and 5 rupees for table. Now in order to solve the problem, let us assume he prepares x1 chairs and x2 tables. So first of all we see what is the objective of the manufacturer. Obviously it is to maximize the profit. So what will be the profit? X1 number of chairs, profit per chair is 3. X2 number of tables, profit per table 5. So total profit will become 3x1 plus 5x2. So we write Z equal to 3x1 plus 5x2, which represent the profit. Now one will always interested in maximize profit. So objective function is maximize Z equal to 3x1 plus x2. Now here we can see when x1 and x2 take higher values, the Z will increase, we get more profit. But here are some restrictions, which are hours available of machine A and B. So we see here, first of all we take machine A. So x1 chairs required 2x1 hours, 4 tables required, x2 tables required 4x2 hours. So 2x1 plus 4x2 must be less than equal to 16, because only 16 hours are available on machine A per day. Similarly, x1 chairs require 1 chair requires 6 hours of B, so x1 chairs will require 6x1. Similarly, 1 table require 2 hours of B, so x2 tables require 2x2 hours of B, and total available hours are per day are 20. So 6x1 plus 2x2 is must be less than equal to 20. So this is our objective function, which we have to minimize Z, and the conditions are these two conditions. Under these conditions, and along with x1 x2 greater than equal to 0, which is obvious because the number of chairs and tables cannot be negative. So this is the mathematical form of the given problem. Thank you.